Welcome to This Explainer. Today, we are unlocking a fascinating, completely hidden world. Look around the room you're sitting in right now. You probably think the only computers nearby are your phone, or maybe your laptop, right? Well, the truth is, a modern car alone contains over 100 invisible, single-purpose computers silently running its systems. You are literally surrounded by dozens, maybe even hundreds, of invisible computers quietly running our modern world. They're called embedded systems, and they're absolutely everywhere. So let's dive right in and uncover the hidden technology powering our everyday lives.
Okay, so here's our roadmap for today. First, we'll cover embedded basics. Second, conceptual design. Third, digital brains. And finally, world connections.
Let's kick things off with Section 1. What exactly is an embedded system?
To answer that, we first need to ask, what even is a system? Well, a system is simply an arrangement where all the assembled units work together according to a set of fixed rules to accomplish a specific task. Think of the tiny gears inside a mechanical watch. Every single cog is a component following strict rules just to accurately display the time. And here's the absolutely crucial point. All these subcomponents depend on each other. If just one tiny gear fails, well, the whole watch stops working.
Now that we know what a system is, what makes it embedded? Basically, embedded means something is attached to or part of a larger thing. So an embedded system is essentially computer hardware that has software permanently embedded or, baked right into it to perform a very specific task. An ATM is a brilliant illustration of this. It's a complex piece of hardware for sure, but its software is strictly dedicated to handling financial transactions securely. It doesn't browse the web, it doesn't play video games, it does one thing, and it does it exceptionally well. Another fantastic everyday example is your washing machine. This highlights a couple of key characteristics we need to talk about. First, it's single-functioned. It's designed to wash clothes, period. Second, it operates in real time. Embedded systems often have to react to changes in their environment immediately, without any delay. Think about it. When the washing machine's water sensor detects the drum is full, the system has to compute that result and shut off the valve in real time, or else, well, your laundry room is going to flood. Plus, it's tightly constrained to be cost-effective, use minimal power, and actually fit inside the appliance.
Underneath the hood, every embedded system has three mandatory core components. First, you've got the physical hardware. Second, the application software, which provides the specific instructions for the task. And third, something called an RTOS, or real-time operating system. You can kind of think of the RTOS as the ultimate project manager. It supervises the application software and schedules exactly when processes run. It sets the strict rules during execution to control latencies and prevent delays. Basically, it ensures the system reacts exactly when it needs to.
Moving right along to Section 2, let's look at the conceptual design, or what I like to call the brain and body.
So let's lean into that brain and body analogy. At the center of every embedded system is a controlling device. This is the brain, and it's completely hidden from the user. This brain receives input from peripheral devices, which act kind of like its senses, things like buttons, microphones, motion sensors, thermometers. The brain processes that info using its detailed instructions, and then it commands the output peripherals, its limbs essentially, like LCD screens, speakers, or motors, to take action.
To make this brain and body function together, there's a constant interplay between physical hardware and virtual software. Sometimes it's hard to grasp the importance of programming because software is entirely virtual, while the hardware is, well, something you can physically hold in your hand or drop on your toe. But software design is really just the art of creating intricate patterns of zeros and ones. These binary patterns act as signals telling the physical hardware exactly what we want it to do. Both parts are equally critical for a successful, optimized system.
That brings us to Section 3, digital brains, processors versus controllers. At the core of the brain is the CPU, which is constantly fetching, decoding, and executing instructions. But exactly how it fetches that data depends entirely on its architecture. There are two main types here. The von Neumann architecture fetches both its instructions and its data from a single shared memory space. This can sometimes create a bottleneck, which limits operating bandwidth. On the flip side, the Harvard architecture uses two completely separate memory spaces, one for program instructions and one for data. This separation is great because it improves bandwidth, since the CPU can fetch both at the exact same time.
Now, depending on the job, engineers choose between two main types of processors, the microprocessor and the microcontroller. Think of this as an epic battle between the generalist and the specialist. Microprocessors are the generalists. They are multitasking powerhouses capable of running your entire computer, letting you play music while typing a document. Microcontrollers, however, are the specialists. They are intensely task-oriented. Remember our washing machine? That relies on a microcontroller perfectly engineered to do nothing but wash clothes.
The really crucial difference comes down to how they handle memory and resources. Microprocessors require external memory, like external RAM and hard drives. That makes them heavier and incredibly fast, sure, but also much costlier and super power-hungry. Microcontrollers are a totally different story. Their RAM, ROM, and I/O ports are embedded directly together on a single chip. Because the memory is fixed and limited, they are incredibly lightweight, much cheaper to mass-produce, and consume barely any power at all, which makes them absolutely ideal for specialized embedded systems. And finally, Section 4, Connecting to the World. How does this isolated digital brain actually interact with our messy analog reality?
Well, it does this through peripherals. Peripherals serve as essential accessories that help the processor out. We are going to quickly run through 6 vital ones: GPIOs, timers, ADCs, DACs, UART, and PWM. Now, some of these are external, added on later, but a lot of them are on-chip internal peripherals built right into the microcontroller itself.
Let's start with the foundational gateways, GPIO, which stands for General Purpose Input and Output. If you ever look closely at a microchip, you'll see these tiny metal legs or pins sticking out of it. Those are often GPIO pins. They can be programmed by a controller to act as inputs, meaning they read an incoming voltage level, or as outputs, pushing out a voltage to represent a 1 or a 0. They're basically the primary doors in and out of the digital brain.
But here is a major problem. The real world isn't digital. It's analog. Temperature, sound, light, these are continuous flowing signals. You can't just plug an analog thermometer directly into a digital GPIO pin that only understands absolute zeros and ones. So this is where the ADC, or analog to digital converter, swoops in. It acts as a vital translator. It takes those real-world, continuous analog signals and converts them into pure digital numbers that the microcontroller brain can finally understand. The ADC pulls this magic off in 2 steps. First, it takes that smooth, continuous analog input and performs sampling, meaning it takes quick, rapid-fire snapshots of the signal's voltage at specific intervals. Then it uses quantization to round those snapshots to the nearest digital value. The end result is this staircase-like digital output that safely represents the original real-world signal so the computer can process it. Okay, now let's flip the script. What if the digital brain needs to create a real-world analog effect, like playing a song through an audio speaker? For that, we use a DAC, or digital-to-analog converter. The DAC takes the digital integers, the pure math produced by the processor, and translates them back outward, converting them into flowing analog signals that can physically drive things like AC motors or analog audio equipment.
Here, we can actually see the DAC process in action. It takes that blocky digital input, passes it through a holding circuit, and then performs something called wave smoothing. It essentially sands down the rough digital edges of those zeros and ones to perfectly recreate a smooth, continuous analog wave. It's kind of like turning a really pixelated image back into a perfect, smooth painting. Besides talking to the analog world, microcontrollers also need to talk to other digital devices. A super common way to do this is using UART, Universal Asynchronous Receiver Transmitter. What's really cool about UART is just how beautifully simple it is. It's a hardware protocol that transmits data serially, one single bit at a time. It's incredibly efficient because it only needs 2 wires between the devices, one to transmit and one to receive. It's like the ultimate digital whisper between machines.
Finally, we have PWM, or Pulse Width Modulation. Remember earlier when we said digital pins can only output an absolute 0 voltage or maximum voltage, like 5 volts? Well, what if a motor needs exactly 2.5 volts so it can run at half speed? Since the digital pin can't magically output a middle voltage, we kind of just cheat. We use PWM to rapidly turn the pin completely on and completely off at blazing speeds. By modulating how wide the on pulse is compared to the off time, we create the perfect illusion of an in-between voltage.
We call this the duty cycle. Let me give you a concrete example you can take away. If we have a system operating at a maximum of 5 volts and we program a 50% duty cycle, meaning the pin is on half the time and off half the time, really fast, The external device is going to experience an average output voltage of exactly 2.5 volts. It's just a brilliant workaround for a purely digital device to achieve highly nuanced variable control in the real world.
Wow. So we've covered a lot today. Everything from basic systems and strict RTOS rules to Harvard architectures and the clever tricks of PWM. Before we wrap up, I want to leave you with a provocative thought. Now that you know what an embedded system is, and you know there's a specialized brain inside almost every electronic device you own, just look around you. How many unseen microcontrollers are quietly sitting in your home right now, just waiting for your next input? It's wild, right? Once you start looking for them, you realize you are never truly alone. These invisible computers are everywhere. Thanks so much for learning with me today on This Explainer. Keep exploring,